This is Mr. Martin. These are the video notes for Geometry Honors, section 10.2. We're going to be talking about congruent chords today. So make sure you're getting through all the homework problems. If you don't think you're going to have enough time, make sure you start from the last problems and work your way backwards. That way you're sure to do the harder problems in the homework. So anyway, let's get on to the two theorems of this section. The first one says if two chords of a circle are equidistant from the center, then they are congruent. And remember, when we see this word equidistant, if you remember how we see this in proofs, in a proof, this is shown by congruent segments. So if you see a pair of congruent segments, that's going to indicate to you equidistance. So you're not going to actually see the word equidistance in there. So let's take a look at a picture. So we've got a circle, and here's our center, and I've got a chord here, which I'll call AB, and I've got a chord here, which I'll call CD. And let's draw in the distances. Remember, the distance from the center to a chord is the perpendicular distance, so I go perpendicular to each chord. I'll call this point E. I'll call this point F. All right, so the hypothesis says that if two chords of a circle are equidistant from the center, so if we know or can prove that, let's make the center of this O, OF is congruent to OE, then we can use this theorem to conclude AB, one of the chords, is congruent to CD, the other chord. So these are our chords right here. Okay, two chords of a circle are equidistant from the center. That's OF congruent to OE. Then we can prove that the chords are congruent. You're going to be using these a lot in proofs and in algebra problems. So again, if you have any questions, make sure you write them down so you don't forget to ask. Or if you're watching the video in class, go ahead and ask me right away. All right, moving on to the second one. If two chords of a circle are congruent, then they are equidistant from the center of the circle. So basically, we're going to have the same picture. Now we're just looking at the converse. So I've got chord AB. I've got chord CD. Here's the center of the circle. Here's the segments that represent the distances from the center to the chords. Remember, they're the perpendicular distances. So we'll call this point E again. We'll call this point F. Make the center of the circle O. So now for this one, if we are given or can prove AB is congruent to CD, so now we're starting with the chords congruent, then we can use this theorem to prove OF is congruent to OE. So basically it's the converse. So now we're starting with the chords and we're proving that the distances from the center are congruent. So again, make sure you ask me any questions. Let's move on to the examples. So we're given circle O. So just to clarify again, when you see circle O, you know that O is the center. Basically, that's what that information tells you. And we're given that AB is congruent to CD, so we're given that the chords are congruent. And we're given an expression for OP, and we're given an expression for OQ, and we want to find the length of OP. So Since these two chords are congruent, we know that they're equidistant from the center, which means that OP has to be congruent to OQ, which means that these expressions have to be equal to each other. So I've got 12x minus 5 is going to equal 4x plus 19. So I'm going to subtract 4x from both sides, so I get 8x minus 5 is equal to 19. Add 5 to both sides. 8x is equal to 24, which means that x is equal to 3. So once I get x is 3, I can solve for segment OP. So that's going to be 12 times 3 minus 5, which, if I'm doing the math correctly, is 31. All right, so just a pretty straightforward application of one of our theorems that if the chords are congruent, then they're equidistant from the center. Moving on to example 2, if you want to go ahead and pause the video for a second, I'm going to pause my video and work out the solution, and then you can check to see if yours is the same as mine. Otherwise, you can go ahead and keep the video rolling, and it'll pop right to the solution so you could see. But I encourage you to pause the video right now. All right, so here's the solution to the proof here. Since we're given that triangle ABC is isosceles, in step 4 we can say that AB is congruent to CB, because if a triangle is isosceles then its legs are congruent. And we can see that AB and CB are chords of the circle. And since they're congruent chords, that means they have to be equidistant from the center. So that means that PQ has to be congruent to PR. If two chords of a circle are congruent, then they are equidistant from the center. So again, notice that this equidistance is shown here with congruent segments. And then once we get the distances from the center that are the same, PQ congruent to PR, those are two sides of that triangle that we're trying to prove isosceles, and since they are congruent, we know the triangle is isosceles if at least two sides of a triangle are congruent, then it is isosceles. So be careful here, don't write if the legs of a triangle are congruent, because we can't say that they're legs until after we've proved that they're isosceles. So just a little reminder there about that. So again, as always, if you have any questions, make sure you ask me, and we'll see you next time.